So our third speaker in this session is V. Balajan Viswana Fan from Condor Computing. He has over 25 years of experience in verification. He holds a BS degree in ECE and a PG diploma from the University of Texas, of Austin, sorry. University of Texas in Austin, sorry, on AI ML. Viva's domain expertise includes RISC-V, ARM, x86, CPU, GPU, load store, cache coherency, memory ordering, shader core, coherent interconnect, CHI, DDR, and LPDDR, memory controllers, random instruction generation, constrained random, and formal verification. It's a good list. And Vibharajan is going to speak about memory patterns, reusable stimulus for RISC-V memory subsystem verification. Okay. Okay.
That's a long introduction. Thank you, Mike.
Thank you.
This is the last presentation before lunch. I hope I'll make this really quick and also make it, I hope, interesting. So this is called memory patterns, and there are a lot of slides, and most of them I intended to be reference slides. I'm not going to go through each line item in the slide. So maybe after the session, if you have any questions in the slide, I'm available to talk. Let's try to cover it as soon as possible. So we're going to cover memory patterns is the idea that we actually tried on our load store verification. But first we'll actually try to see the overall memory subsystem verification and challenges. And then the memory patterns, what are they, and the details about it, and then some results. So first, let's see the overall memory subsystem verification scope and some of the challenges. So this is a typical SOC diagram with the CPU clusters, all the caches in place, and memory controllers, and sometimes you get the traffic from IO subsystem as well, GPU accelerators, they can generate coherent traffic. So I just try to capture the overall memory subsystem if you're going after caches, coherency, and all of that to verify them. So I hope this kind of gives the overall idea. So RISC-V, since the focus is going to be on a load store, what are all the different load store instructions that we are supporting, right? This slide summarizes the different loads and store sizes. I'm not going to go in detail. This is a typical L1 cache organization, right? I put this slide just to appreciate the complexity of it, right? I mean, when you're actually trying to verify that L1 is part of the load store, the banking architecture, and then different sets, and then the tag to verify, and then how do you actually create a hit and miss scenarios. So just to appreciate the complexity, I put this slide here. The overall verification scope. Again, this is the pretty busy slide. I'm not going to go through all of them. But if you try to look at it, on the left-hand side, load store and the caches on the right-hand side, and the load caches are actually 64 bytes cache line size. So all the loads and stores are going to be 64 bytes. But on the load store, the max size is 8 bytes. So you would need to do 8 accesses to cover the whole cache line, right? And there are aligned, unaligned cases, right? And then sometimes your load store pipeline, it interacts with the MMU. And then if MMU is actually a page miss, your pipeline is going to get affected, right? And then there are more complex features, branch prediction, speculative execution, all of that interacts with the load store, right? Data forwarding, right? Besides the major topic everyone think of, coherency and memory ordering, right? These are all the features that you're supposed to actually focus on, right? And on the cache side, yeah, you look for cache hits and miss and snoops. And I'm not going to go in detail. Sometimes in the multi-core scenario, false sharing, true sharing, that can affect your coherency, right? And create a lot of snoops, right? And it affects the traffic as well, right? On the bus, creating the out of order response scenario, right? That can affect your pipeline, right? It can create stalls on your CPU machine. So how do you actually create them? So I hope this summarizes the overall verification scope and the challenges in the memory subsystem. Let's jump to the memory patterns. That's the main idea of the paper, right? What are memory patterns? I worked on a DDR controller a long time ago, and then the caches, and then now the load store. So I got inspired with several verification patterns. So now this actually try to summarize that kind of a patterns that basically can be done at all level: load store, caches, and the memories. So that is the idea. So what are memory patterns? It consists of access patterns and the address patterns, right? So the simple terms is it's a collection of loads and stores accessing a continuous memory range without leaving any holes in a particular address pattern. It could be progressively increasing or decreasing. Sometimes you repeat the same address as well, right? So that's pretty much it. That's how I call it as a memory pattern. And it consists, as I said, access pattern and the address pattern. So what is access pattern? Access pattern could be address dependency scenarios, register dependency scenarios, collision scenarios, etc. There is more exhaustive list on the rest of the slide we will cover. And like I said, address pattern could be progressively increasing or decreasing address, or sometimes it's a user-defined type. If you're trying to instrument a specific scenario and then you want the address to go in a particular fashion, let's say prefetcher. Now you want to have a bunch of addresses going on a single thread, right? So things like that, right? And then the last one is the step size. Again, it is configurable. You could have it as a, like I said, progressively increasing, or it could be a increment on the set index or a cache tag. So you will start seeing a lot of cache behavior as well, right? So I hope this gives a little sense of what are memory patterns. Let's look at more in the rest of the slides, right? So over the next few slides, I'm trying to introduce some snippets of the memory patterns, right? How do you create address dependency, right? If you have two stores, you put the same register and the register has same address. So you're going to have you're writing to the, there is an address dependency right there. Or sometimes, again, these are all pseudocode. Please don't look for assembly mnemonics corrections. But I hope it tries to introduce a few ideas, right? And then over here, two different registers, but they have the same value. So there is a address dependency. On the right side, register dependencies. So you think of raw, var, write after write hazards. So all of the hazards, part of the register dependencies. And sometimes there can be more, right? I mean, I'm trying to, we have something new called the single or multiple dependencies, right? So when you have a store here whose operands are given by two instructions in the top. So this is dependent on two instructions in the top. So this can be stalled when both instructions or any one of that actually stalled, right? So single level dependency is like just one operand coming from the previous instruction, right? Simple concepts. And then different pattern, right? How do you create continuous address, right? Especially with pick a same type of load and try to create continuous address, right? So you can change it using the offset, or you can actually increment the register content. And in RISC-V, you'll have to do it with using an add instruction. You cannot do it like this, but you can do this one. So this is actually progressively incrementing, right? So and all the load sizes are load bytes. So like I said, continuous address range without leaving any holes. So the next instruction increments by 1, right? So on the far right-hand side, there's a decrementing case, right? You start with the larger address and you keep decrementing, right? And over here, it has earlier we saw only one type of load. Here it is a mixed type of load, right? Different size of the loads. And then in which case, your next address is added based on the previous size, right? If the previous size is 2 bytes, and then you add 16, or 2, yeah. And then this contains a mixed stores, right? Let's make it a little more complicated. How do I mix loads and stores, right? On the same way, continuous address. Simple patterns, and then do loads and store mixed continuous addresses, and how do you create two-level dependencies like we talked about in the past, right? So yeah, those are some of those different variety of patterns, and this one creates especially overlapping and collision scenarios, right? Where the next instruction starts half the size of the previous one, right? And that's where this -2 by 2 that kind of exists, so that you create collision scenarios, right? So I'm going to move on. Those are some of the patterns. So now we saw different patterns, and how do you create a test? So the option is, there are 3 builds, 3 options, essentially, right? The option 1 is pick one of the patterns that we created and then put it in the patterns bin. And then you pick option 2, which is the address pattern. Could be one of that, increment, decrement, or both address patterns and the step size. So you pick the address pattern and the step size. And third option is some of the common options. It could be how long you want the test to land, and then is it actually going to be aligned or unaligned and things like that. So you throw in the third option, and there you go, you create the test, right? And the power of it is everything becomes, if you have like 10 patterns and then like 5 different addressing scheme and then like 2 different options, it becomes like 10 by 5 by 2, that many test combination that you can create, right? And so these are some of the test scenarios, how you can create using the patterns. I try to enlist some of them. I think I do like to go through this just to appreciate how the patterns help. So if you have the same loads to the same cache line, everything is a miscondition, right? What you will see on the bus side is a single memory access because you're covering the same cache line, right? And then if you do the stores to the same cache line, you will have a single memory access, and then all the stores needs to be merged in order, right? On the within the LSU, right? And then loads and stores to the same cache line. When you mix loads and stores, you will start seeing data forwarding scenarios. If a load comes after a store, then store to load forwarding starts happening, right? And then with the address dependencies, when you create, especially store addresses taking more time than the load, you will start seeing speculative, right? And data as well, right? And then loads and stores with registry dependencies, you will create all the hazard scenarios, right? And on when you create all hit conditions, especially the loads and stores are continuous and overlapping, you will start seeing, it doesn't matter to the same cache line, but because they're all hit, you'll start seeing data bank crossing, bank collision scenarios when accessing the L1 data cache, right? And if you, in the address pattern, if you change if you pick set index as an increment size, you will start seeing LRU evictions, right? And if you have them in a circular address pattern, you will start seeing continuous eviction between L1 and L2, and also reallocation, right? So those, I hope that gives a sense of how we create the stimulus, right? So those are the memory patterns, and they are scalable, configurable, and reusable. We have written them using Python, and it's all targeted to the LSU at the full core level, right? And we could actually instrument it for unit level and subsystem level. It's a test generator. You can actually map them to unit level. And so currently, we are in the middle of the verification. We keep doing a lot of tests. There are about 300 generator tests, 100 plus explicit tests. that we initially generated them, they are more directed. We get about 70% fails on the generated test. So I would like to thank Kiran, who is at the backside. I mean, he's the overall full core lead for implementing this. We shared ideas and the overall partnership. That's all I had. If you have any questions, I can take them.
Are there any questions first from the audience? You have one? Yeah, one question, please. Do you just want to introduce yourself before you start, please? Yeah.
Hi. So how much of this memory
Yeah,
patterns
can you
are-
just introduce yourself?
Oh, this is Manish. I'm an intern at AMD. I'm working on DB. So I would like to know how much of these memory patterns are really mimicking in the real world memory access patterns, like in the general real world CPU or whatever it may be in today's trend.
So just that's a very good question. So are you asking what are the already being used for verification? Is that what you're asking?
No, you're talking about the memory patterns, right?
Right.
In concept of verification. So in today's world, like in the today's CPU trend, how much of these patterns are generally being really accessed by the CPU to the memory?
I think all of it. I mean, that's the reason we created all of them.
Oh, is it like
right?
100%? Like, I mean, not every pattern needs to be accessed, right? I'm speaking about
For
trend.
example, yeah. So depending on what kind of a CPUs that you're working on, high performance or not a core, right? Some may not be applicable, right?
Okay.
But these are pretty much generic patterns.
Does this support out of order as well, or just the not?
It supports out of order.
Okay.
Hi, my name is Puneet Singh, and I'm in the design community and verification community. So I had a question, which is probably, kind of like was there any kind of this based on global test plan for full chip and sub-level, like the fails generated, and is that any kind of like learnings from getting the generated content back, in a recursion way to get more, of the high level goals?
Yes, yeah, that's a very good question as well. So these tests are actually done at the full core level, targeting LSU, and we are already thinking of MMU patterns or rest of the CPU engine. You could actually have any repetitive patterns. So you need to actually write them as in the form of a pattern. Maybe it's not called a memory pattern, right? So then you can actually do it in the same kind of a methodology. Yes, that's possible.
Okay.
That answer your question? Okay, great.
Any more questions in the room? Yeah, sorry, just one over here.
Hi, this is Krishna from Intel. Do you consider gather and scatter as memory patterns?
Yes,
Ah.
they are there. They're also part of the memory pattern. Actually, all of I've not covered all of them here. All the register hazard patterns is part of the memory pattern.
Okay, I think there are questions here. So just thank you very much.
Thank you.
Thank you.
Thank you, Mike.